Hi, perhaps one of the things that you are having problems or it is not correctly understood is the idea how to start developing circuits, okay? Developing and running, because in this lesson they go very tight and they go together and they have to be solved step by step. So this is the point. You have the lesson and the projects in P9, both, for example, the one digit BC, the other in one hand, which is a complete project, and then you have the other one, the dual MOOCs 4, okay, which is the same, section by section. And this means that you can, above all, you can copy and adapt that problem to the new exercise or the new project that you have ordered to solve, okay? Because it's strictly the same idea. Whatever you are going to learn solving the MOOCs is the same that now you have to apply in the next project. For example, here, if you have given this picture, you naturally have to solve a hexadecimal to 7-segment decoder, okay? 7 outputs and 5 inputs. So what exactly are you going to do to solve this exercise? How to start, The idea is the same as always. Let's specify and plan and develop and test. But now, if you like to be practical and you like to save a lot of study time, you have to make something correctly from the very beginning, okay? And this thing is to go step by step. So this is what I will record now for you, okay? Let's copy and adapt something that exists, imagining that everything has been already organized and planned. So, okay, let me explain you how to start this idea of developing and testing at the same time from a given example, okay? That is going to be the main idea here. So the objective now is not go and finish the circuit just in one step. Forget that. It's about, doing it in a way that from which you can learn and you can modify, and then you can learn a little bit more and you can go and write a little bit more code and all the time the same way. So the first objective is going to be, set up the hardware and software development environment. I mean the Proteus hardware environment, this virtual lab where you have the real circuit there, the model of the real circuit, and buttons and resistors and the like, and 7-segment display, so everything you need for building the hardware. And at the same time, in this development environment, you have the software section, the integrated development environment from MPLAB, okay, X, that goes together with a compiler. So you have this environment and you need to know that this is going to work. For what exactly? Well, if you have in mind the building of a complex circuit, let's imagine a hex 7-segment decoder, a complex because you may say here that you have a lot of inputs and outputs to read and write. So the idea here is very simple. Let's take it easy and let's forget that this circuit has that many number of inputs and outputs, okay? Let's consider a single one. So you have seen that, for example, you may like to connect a button, okay, a blanking input button, which is going to be 5 or 0 volts, to a given port pin. For example, as the exercise says, the pin 1, okay, the pin 1 in the port A. So that is enough for you now, because you have in mind to go and test the reading of this pin and to see if the software runs correctly. So you can go and add later, step by step, one instruction after the other after having organized them by means of flowchart and memory positions. So for example, if this is the pin, okay, blanking input, the purpose of reading and pulling is that idea of convert, okay, let's convert the pin into a convenient variable. So the pin is not going to exist anymore when you are reaching the truth table section of the code, but is going to be transferred to the RAM variable, okay? A convenient RAM variable, and we name them all the same way, var bi. And this means that you will you will devote a char, type variable, you know. So all the bits are going to be zeroed except the bit 0, where is going to be the external pin saved. Okay, so that is the idea. And now what goes next, you know, is to think about copying an example from the digsys web and adapting in this way. You know, the next step is going to be rename the tutorial and generate the folder, okay, and copy the hardware and the software files, as you will see now, and then, you know, leaving only the functions, for example, write outputs and through table, where you don't have to do anything now at this stage. So comment, you may like to comment them completely and leaving only the name of the function, but no code inside, in a way that you are going to occupy only about the reading of a single pin in a given port of the microprocessor. And this commenting idea is going to be also here in the init system, but in read input and init system you will comment not all, okay, all which do not attain, all that is not attaining, you see, what? The port A, you see. So whatever that is not the port A is going to be commented. That's the idea. So get and copy all the hardware and software and occupy, in this case, only about, you have to occupy yourself only about the single pin of a single port with this very clear idea in mind. Get the variable. And once the lesson is learned, this is going to work, you know, by watching the variable in a window. You will be clicking the button and the variable will change, you know, continuously. And once this thing is going to work, you can add new or different pins. Okay, later when this first step and this first objective has been reached, you can add more inputs, or you can try to write something. And again, this time, if it's the first time that you will go writing, your purpose is to write a single pin, for example, the output A. That's enough. All right, writing the A, Liri, and you know, testing that these ones and zeros in A has been converted into light, no light, into a 7-segment display, for example, I don't know, a common cathode display. That is going to be enough, in a way that later it's not going to be a problem to recopy and readapt it and learn the lesson to write other ABCDs and so on and on. Okay, so that is the initial idea. So the first thing is to go to the tutorial project, the DualMux4, and let's go down to this time to the development section, you know. Okay, and here is where you find the DualMux4 that has to be saved as, you know, in your unit with a corresponding name. So this is going to be a new project. Okay, this is what you've got in mind. The project is a hex 7-segment decoder. All right, that is the name of the project folder in P9. And now you know the name of the hardware is going to be the same, hex 7-segment decoder. All right, so that is the hardware file for your new project, something that already exists and is working. And here you are the software. So let's copy it as, but you know, in the same location, but with this new name. Very well. So that's the starting point. Okay, now you have a computer where the disk is showing you the unit, you know, CSD. In CSD you have the P9 with this new hex to 7 segment decoder with the 2 files that are of your interest. Perfectly well copied from the web. So now if you organize the full project, it has to work because that is from the web and has no errors. Okay, so that is going to be the purpose now. Let's go and switch on the MPLAB X environment. And let's attach to this new environment the C file, the hex 7 segment decoder file. Okay. So let's get rid of the start page and file, new project, and a standalone project for the PIC 18F4520 chip. Next, the hardware tool doesn't matter very much now because we are going to solve that using the Proteus environment. But here, yes, you have to say that you are going to use the XE8 software environment, software compiler, C compiler. So now you know very well where the project is located. So this PC, L, CSD, P9, and the hex 7 segment decoder. That's the name, right? So you copy the name if you like. Open this as the project location, and now the name, you know that is the same, but PRJ. That's the way we do it from the very beginning. Now we are going to leave the project folder that has been generated automatically, the .x as it is, and let's set that as the main project, and let's say finish. And at the same time, if you like, you can click the hardware, because both windows are going to be working together. The compiler will generate executables and the Proteus is going to execute that software, right? That configuration file. So you have this chip, and perhaps now if your turn, you know, you can get rid now of something here. For example, you can get rid of something. There is no need to change it all now, but you are focusing your attention in a single pin. So now you can leave it as it is, okay? And you only have to go and change this by BI. That's the new input in which you have interest, okay? And then the chip now is the dual MUX 4. So what you have to do now is to go to the child sheet, okay? You have to copy everything onto the clipboard. So you see, copy to the clipboard like this, and now you go again to the top, and now is your turn to change the name. Instead of dual MUX, you know, it's a hex 7 seg decoder. That's your idea, okay? So now you go to the child sheet and paste it all from the clipboard. So now you've got it the way it has to be. A new project inherited from a previous tutorial. And as I say, you can get rid of these because now it's not about channels. Whatever, but now doesn't matter very much because you only have this interest, because that is just the very beginning. So you have to go to the child sheet and be sure that this BI, you know, this you can disconnect this wire here, and this is going to be the BI, okay? And you have to make the connection to the BI to the R1, okay, like this. All right, you can get rid of any inconvenient wires now, but you see, this is your only interest now. Connect to the R18 A1, you need the pin 1 in the port A, this new value. This is what you like to do, okay? So this is the hardware, and then it goes the software here. So now we can go back to we can save that. It's going to be saved correctly, so you can continue later modifying the hardware. But now you are here in this environment where you have the project, and now you have to add a source file that exists as well. So let's go and do it. Add existing item, which is just one level above the decoder. C, select, okay, and now is your turn to go and modifying this. But before doing anything, it is a good thing to set up the right properties, which have to be which has to be that one. You know, you have to go to the XE8 global options and say that is going to be a C90, and the COF is the output file format for you. You say okay. And now, because this it's already finished, the only thing for you is to clean and run. Okay? That is what is required at this stage, to be sure that everything works fine. I mean that the software environment is capable of generating whatever the number of warnings, the final COF, the one that now you are going to connect to the, you see, this is the one that you are going to connect now to the hardware. So you've got the hardware here, so you say edit properties. So now is your turn to go back to this computer, L, CSD, and now the P9 location hex 7 segment decoder, and go to distribution, default, production, and this is the COF that has been generated just right now. Okay, so you say open the file, and now you say okay, pay attention to the processor speed, 4 megahertz. So you say okay, and you go to the top, and now it is very important for you to run that, you see, and see that there is no errors. Okay, so very well, the system is animated, running in real time. But you know, that is not your problem yet. But let it be like that, okay? Just reading the blanking input so that we can convert this pin into a convenient RAM variable to be watched in the watch window. So now you can stop, because everything has gone right. You can stop the simulation, and you can go back now to the software environment. And here is when I say that you have to be tactical. You know, this is another program. It has been inherited. So now is your turn to delete the comments, and here is where you have to add your own commenting, you see, add your comments and everything, contextualize the problem, and then, you know, include don't have to be modified. You have to leave the function prototypes as they are, and here, for example, you will comment it all except the variable of your interest, right? So this is what you are going to do, because here you see, comment it all like this, but this variable is going to be the var bi. All right, let's continue. Well, let's keep one of the buffers or two, that's not important. But then in main, you see the main is going to work perfectly well, because you are not going to change anything here. That is exactly what you want, and this is why you copy something similar from the web. And then here in the Init System, you will leave the configuration bits as they are, so do not touch them. There is no need for doing so. So now you see, where is connected your blanking input? In the port A. So this is where you have to pay attention when modifying. The other has to be, you know, cleared. So you simply mark it all as a comment. In this way, this is not bad text. It's not software anymore. So the same with read inputs. Okay, you can very well now mark it all, whatever it is internally in these read inputs. Let me see if I can do that correctly. You see, you can mark that section of reading inputs except if you like that I see something here that is attaining the port A, so I will leave that, okay? But whatever else is going to be not. It's going to be commented as text, okay? So in this way, you have nothing at all. You see, nothing in the port C, nothing anywhere, just text, all right? You have something here. That is going to be your starting point. You see, this has been detected as a non-identified item, so very well. Let's comment the same. So, okay, the bar buff, because you have to leave it as a definition, it can be used. So now you can go to the next function, truth table. Naturally, this is the truth table, the flow chart, the behavioral interpretation of the truth table of the dual move. So this is not of your interest, so, and comment it. And the same with writing. You see, you are not interested now in writing anything but reading a single pin. So do that thing. You see, you have a computer code that is very simple. It contains only 2 instructions that you know nothing about them now. So that's not going to be a problem. So you run, you clean, you see what you have to do. You clean and build again the main program to see if you've got 0 errors. Very well. Okay, so now what has happened here is that your hardware, okay, that was already attached to the COF file, it is running the same, but it is running with this new software. So everything works fine. So now is your turn to go back to the hardware, to the software, and do what you have to do to read this variable. Okay, is that so? So let's see what we have planned about it, because that if now you have to type that code here in, you know that I say all the time that is impossible to do that without talking first and organizing first the flow chart, even for a single pin, and that is precisely the point. Okay, this is where we are now. We have modified conveniently and commented all the sections of the code except something that was left in the read inputs and something that was left in the init system. Basically, what was left was connected to the port A. This is where we have interest now, okay? So let's go one by one. First of all, you have to declare in init system, the first modifications of all has to be like that. In init system, you have to do something, okay? Which is configuring the port A bit number 1 as input. So to do that, now you know that there is a shadow register here, which is called trace A, and here is where you are going to write a 1, so that this port A pin bit 1 is going to be declared as an input, and by default the others that are not in use are going to be converted into output by definition. So that is going to be the idea now. Let's organize the trace A like this, because that is the point. You are not interested in anything about the port A except the pin 1. Where is that you have the pin input? Okay, so this is what you are going to do in the init system. Okay, and then what goes next is to discuss what is going on in read. So what you have to do, okay, if you've been studying the tutorial carefully and the previous recordings on reading and writing and the previous slides, you will see that now the way we do that thing of reading is very convenient, First of all, if you talk about read, if you talk about read, you know that first of all you have to organize the software. For example, read all the bits, all the port A bits. That is the idea. In this way, you take them all inside the computer as just in a given convenient variable. For example, bar buff, all right? And that is the time when you sample the inputs, when you do that idea of reading them all. And then what? Well, you have to go and mask the bit, the single bit of interest, okay? You have this idea now, the bit of interest. That is what you have to do. And then you have to imagine what goes next, but perhaps you can solve that, so I will delete that idea here because it is very simple, okay, to translate into C code, a single writing into the trees. So now here we have some space to develop this flowchart into memory positions and into C code, all right? And then it's going to be the time to go back to the software hardware environment and put these ideas into practice. So read all the port A bits. This means that in some way now you will have a convenient bar buffer that has 8-bit, okay, 7, 6, 5, 4, 3, 2, 1 and 0, and you are not interested in anything, you see, except this bit of bit 1. So how can you do that thing of getting this variable? Well, I guess that is going to be, you know, the port A. In order to get this result, the port A is going to be read in one step, you see? So this, if you like now to annotate that in another color in C, is going to be bar buffer equal to port A. That is the instruction for reading, equal, right? Now this is already in the computer as a memory variable. So then what? You have to mask the bits of interest. So now is when you take the mask, and the mask for cleaning this memory position is 0 everywhere except the one here, and what you are going to do is a single AND, okay? So the result of this bit-to-bit AND, you see, bitwise AND is going to be here a memory position, perhaps the same, why not, the same memory position, but just later. So you have all the bits, but this time here you are going to save the bit of interest, okay? This one is going to be saved. Whatever you've got here, okay, is going to be saved because it's going to be whatever with AND 1, it's whatever. But the other ones are going to be zeroed. That is the point of masking. So you have 0, 0, 0, 0, 0, 0 everywhere. Then what? Well, you practically have now what you want. You see, you like to have something like this, 0 everywhere except in the bit of interest. So this is more or less what you've got here, except that now what goes next, you see the next instruction is to shift 1 bit to the right. So you have to push the data 1 bit to the right to be the final one that you like to get here. Okay, so this means that in the end you can have a memory position which is going to be like this, you see? And this is what I like you to do, repeat that, because this is by repetition that you learn better, okay? So 7, 6, 5, 4, 3, 2, 1, 0. And now if you've been, you know, shifting to the right 1 bit, what you get here is precisely what you want, which is this bit at this position. So this is going to be the BI bit, and this is the variable bar BI. So perhaps the only thing now is to invent that in C, but after this micro sequencing of bitwise operations and after this clarification using memory position content, now it is simple, right? Don't tell me if this is difficult for you. Now it's easy to find the code. So you see the code is, as usual, something that has to come immediately without even thinking about it. So if you've got all these pictures now in your paper, it is easy for you to write, for example, another instruction in C, the one belonging to the masking, which is something like bar buffer is the previous value that was bar buffer, you see, and you see that is the ampersand, and then 0b 0 0 0 0 0 0 0 0 0, you see, 0 0 1 0, that's the mask, and semicolon. This is the text that you have to type in the C source file. And finally, the final idea of saving this into the bar and shifting is going to be, you can do again, right? Bar buffer equal to bar buffer shifted one bit to the left. You can do also that, but you can put them together to the idea of saving. You know, perhaps it is not annotated here. Shift, if you say shift, it's not a problem. You may say that bar buffer equal to bar buffer, you see, shifted to the right one bit. That's the idea. And finally, what is left is a final instruction of save. Save. So if you save, now it's your turn to do that in C because it is immediate, right? So this is like writing bar blanking input equal to bar buffer. So you see, naturally, if you have some experience here, you can do all the 4 or 5 operations in a single one. But now it's not the point of this. You are not improving the length of the code or anything. You can do that without even using convenient variables like bar buffer. But you know, this is not for now. For now, you have the single interest of doing it in one way or another, but getting what you want, which is the hardware and software environments running in a way that you can play with buttons and get the results in the right memory positions that you will watch. So you see, now you have something to watch, the bar buffer and the bar BI finally. So let's go to the software environment and do that list of instructions, recompile and run, and so let's be able to go to the testing and debugging section, okay? So after having planned it all, now it's time for placing the code here, okay? So let's just start with the init system. You know, this is initializing the ports very well, the port A precisely. This is something that is of you not of your interest. It goes here because the port A in some way it's also able to handle analog inputs, and this configuration file adconfig1 is where you have to decide if the inputs are going to be digital or analog. So with this code you are making them all digital. So now you have your turn to adjust the trace value. So this is what we have said that has to be, you see, 0 0 0 0 0 0 1 0, right? Something like this. Perfect. So this is what is going to be done. You know, this is for setting the pin direction. 1 means an input, 0 means an output. So now you may say that RA1 or port A is an input. You see, take it easy, annotate the text as well, you know, the comments. If you have to be a good programmer, you know that commenting your program is fundamental. If other people has to read it some years later, naturally, or your colleagues just now. So this is what goes here, right? Take your time to modify the instructions. So you see here, we are defining the pin 1 as an input. So we can continue now to the read inputs, and now is where we go and say bar buffer equal port A. This is read, you see, read all the port pins, okay, Very well, and now let's mask them correctly. So the mask, was something like this: 0, 0, 0, 0, 0, 0, 1, 0. All right, that was the mask of the bit of interest. And then something else. Now you can get rid of this, or you can place that comment a little bit down, and you can comment that another time, because it was about operating again, this time for what? Not, not cleaning the bit of no interest and keeping the bits. What was the idea now? It was about shifting. Yes, it was about shifting to the right one bit. This is why it is a good idea to have documented similar instructions very near of what you are doing. So now that you've done that, and you know the syntax and everything is fine, you see you can swoop that comment, because you have taken advantages of it already. So this is the second instruction. So now the last thing that you have to do, it is going to be very simple. It is bar, you see, I don't know now if it goes with capital. If you bar bi underscore bi is just the value of bar buffer, right? That's it. So that's the final save operation. You see, read the full bit port, mask the bits of interest, shift to the right position, and save. You see, you have immediately a comment here. This bar bi is not identified, so this is because it was defined in capital letters. So that is all, right? That is all. So when you say that the code is not working, I do not understand you, because you see what I'm doing, just a very simple modification to a code that is already running, but now it's my turn to add my code. Just a few instructions at a time. So again, that is the very important thing. I have to clean the previous compilation results and generate the new ones, you see, with 0 mistakes. Very well. So now you see I have a data space which is only 3 bytes, 3 chars. You can identify them very well. I've got here left the bar buffer 2. I remember that. You see the bar buffer 2, bar buffer, and bar bi. Those are the 3 bytes of memory that you can identify here. And you see the software that you are implementing here, the program space is just very teeny, 0.2% of the full capacity of the flash memory of this microprocessor. But those details are okay. But now what is for you very convenient is to jump to the software, the hardware environment, you see, and run, because I remember that the connection was already established here. So now everything has to run properly. But naturally, because it's not about lidis now or anything else, the way to see that it works without correctly is that one. You see, you can go step by step, and you have the windows, and remember that if the windows are not here for any reason, you can get them from the book. CPU, the source code is a window of interest, because in this way you can go step by step. You see the machine is executing functions in the infinite loop, and this is what is very convenient for you. Very well. So now get another window, the CPU variables, and here is where you have the list. You see, every variable is in a different address in the RAM space, and you are interested only in the value. Very well. So now it is time, you see, to add the book, a watch window. Now, so this is the point where you are going to, for example, control or inspect the value of bar buffer and also the bar bi. That is the point. So this is what you are going to check now. Perhaps in binary is even better. So you can change immediately the format of this to show this variable. So you see. And now you say something that practical as run continuously. So this is what you've got. You see. So what is the point of this? So very well. You see now you have a 0. So when you click, you have a 1. All right, look at this. The bar buffer is switching, you know, is toggling, I don't know. You see it more or less, you can see that it is red and that is shift, you see. But that is the computer speed. But you see the bar BI has a 1. This is exactly what we have programmed here. You have a 0 now and you have a 1. All right, guys? So this means that the section of code that you've been inventing here for reading the BI input works very well. So now you can stop and take it easy and go back to the paper section and think about what to do, for example, if you are in this problem, to capture the data input in binary or in hex that is going to be converted into outputs, A, B, C, D. You see, one thing at a time. So I guess that now the next mission for the people who are solving this problem is to get here, alongside the other ones, another variable that is going to be called var D, that will have 4 bits of interest. From the 3 down to 0 bits of interest, the others are going to be 0, and that is going to be the mission, to read. Perhaps these pins are scattered through the ports naturally. I can check that now. So very well, here in the assignment, I can go to the assignment, and for example, I see here that the data 3, the data 2, the data 1, and the data 0 are in PB and in PC, in different pins. So this is what you have to do. You have to organize a variable var D that has to contain the ones and zeros that you have bring from the different pins. Okay, that's it. Perhaps I can tell you something else about the values here. You can stop that and you can use this ideal 1 and 0, or if you like, you can use real buttons. It's a good idea to use real buttons all the time. So you can pick parts from the library and you can pick a resistor. Okay, if it's not, yeah, it is already on the table, but you can pick a resistor when it's going to work. Yes. Yeah, it takes a while, I see. So click the resistor, and then you can pick up a button, right? That way, you click the button, so now you have 2 more components on the table. One of them is a button, and another is the resistor. So now is when you can attach the resistor. You can get rid of this text, that you know that is very simple. You go to edit properties and you add white spaces here. And if doing so, you get that thing with. And now the button, and now you need connections to the power supply as well. You can you know, rotate that clockwise or anti-clockwise, that way. And now it's your turn to add connections to the power, which is going to be understood by default as a 1, you see, and then to the ground. That is what you do here. Now you have an, well, wait a minute, because I'm thinking now in an active high button. So you see, I will place the resistor on the ground side, and the button, I have to drag it. Is, you know, it's that idea. Okay, so this is going to be the connection, electrical connection. Now you've got the wire, and you can get rid of this voltage. So now it's a good turn for you. You see, if you have not a lot of experience of capturing circuits in this Proteus environment, that is your turn as well. You see, so now it is your turn to see that you have a 0 and you have a 1, the same. You see, if it is very well captured, you see that signal in red and blue, a 0 and a 1. You see? Okay? So that's all. It's your turn now to go and continue with this, okay? There is something else that I have to tell you that sometimes is you ask a lot about it, and because it seems that it's not working. When you do that way of going step by step, for example, now if you try to add the variable D or the variable 7 segments, and perhaps, who knows, later, depending on the way that you are organizing this, the bar A, the bar B, the bar C for every single segment, as you like. When you do that, think of adding new variables in the code and, compiling them all, cleaning the previous version of the compiled code and rerunning and regenerating a new compilation. You see, for example, now you have more data space. You see, you have 5 bytes of data space because I had the three initial ones, the bar buffer 1, the bar buffer 2, and now I've got 2 more chars. So this is reflected here. And the thing is that now when you go back to the software, the hardware, and you run, okay, you have the previous window, the previous watch window, and look at this. The bar BI that you were monitoring was the address number 2. Okay, perhaps what happens here now, that if you run, okay, if you run the simulation, when you click the button, you see it looks now that is not working. Do not panic, okay? What has happened here is that this variable has been reassigned to another address automatically by the compiler, because you are not giving specific instructions in that sense to the compiler. The compiler organizes the addresses as it likes. So that is what happened here. So what you have to do, once you have generated a new code, is to stop the simulation, and go to step by step, clean the watch window, because you see now that appears here very well. The bar BI now is the address number 5. So you have to do that thing of, deleting, and the bar buffer is precisely another address. So you see you have to delete. The best way to do that is to clean. That is the point. You just clean them all and drag the new variables that you like, even if they are from the previous example. So you do that thing now, the 4 and the 5, and you run again. You see? So the address, the specific location where this memory is saved, this bar buffer or bar PI, has for you only this interest. To be aware that when you go compiling and recompiling, these addresses changes. So now if you run, you see it works again, okay? All right, it is working again as before, naturally, because you have not done anything but add 2 more memory positions to the system. But you see, the compiler has done this trick of rearranging the addresses. So that is what was left here for you to know. So it's not an error, but something that the compiler does because it doesn't have instructions to do it otherwise.